Yeah, well, anyway, we can.
Awesome. Yeah. Well, I was just actually saying, I guess this is a great way to kind of kick things off. Alain and I met randomly at some like online meetup that was organized for some Polkadot community in Switzerland, like months ago, right? And like we were just I think I was maybe doing some hackathon mentoring or whatever. I was there to like, just chat about Substrate. And I came into one of the rooms where Alain was just very passionately describing what Integritee is, and how the technology can be leveraged in different ways and stuff like that. And I went from like giving other people advice to just being like, wow, this is super interesting, Alain. I need to learn more about this stuff. And then I DM'd you, and then I said, hey, you should come on seminar. But this was months ago, and I think you guys were very busy. But now finally, like it's really cool to have you on seminar. How's it going, Alain?
Very good. Glad to be here and glad to, yeah, I remember it was Trust Square. I think it was
That's right.
this meetup there where we had the chat. Um, yeah, I'm excited to talk about our tech and the possible applications, how it could work, and maybe get some nice feedback. The last time I was here on Substrate Seminar, it was a very lively discussion and very enriching uh, for me as well. So I'm looking forward to this
Yeah,
episode.
sweet. So for those who are joining, for those who are watching this, we're live on Substrate Seminar right now, and I'm Sasha Lansky. I'm developer advocate at Parity Technologies. So my goal and passion is to sort of bring out cool things that are being built with Substrate, and talk about them, especially in this context, and also teach other people, right? Like find opportunities that other people can learn from this. That's why I'm super excited to have Alan here today, because he's going to dive into how they're using Substrate to sort of address their solutions, and like ways that they're leveraging Substrate in like pretty unique ways, right? So I'm excited to get into that. I'm really eager to learn more on all of that stuff. And also, I want to introduce to you guys Alain, who is the co-founder of Integritee. Is that correct? And you obviously are very much involved in the engineering, but your title
Yeah.
doesn't say CTO or anything. But I can only imagine that you are. So do you want to just say a few words about like, so what your role is a substrate in it used to be called Substrate CE, right? But I still get kind of confused. But yeah, what's your
Yeah,
role
yeah.
in
I will.
Integritee?
Yeah. Let me. Yeah.
How did
With pleasure. So, well, my way to Substrate was actually through. I think it was some kind of Event Horizon energy conference, an energy and blockchain conference, where Gav introduced Substrate when probably the first line of code wasn't even written. It was more of a concept. Um, I was very interested, and then when sometime later, I was at the meetup of the Web3 Foundation, and I had this concept already pretty much fleshed out in mind for building Ncointer, this basic income and digital ID proof of personhood system. And so I approached the Web3 Foundation, and there was the grants program. So that was a good opportunity for me and my team to start with all kind of diving into Substrate and building something. Um, and then out of that, we said, okay, Substrate is kind of the idea how Ncointer could provide privacy and also scalability. So this is kind of a building block that is of interest beyond just Ncointer. So this was kind of for the Web3 Foundation the more interesting part, because it can benefit more teams as well. So we started off building Substrate as a framework. It's kind of just open source Apache 2 license, as you're used to from the Web3 Foundation grant projects. And we did that with our team here. So I'm leading a team here at a software engineering service provider, actually. So we developed it on more or less a paid basis in that sense of Web3 grants. But at a certain point, it made sense to say, okay, we can continue with grants, even with Polkadot treasury grants and so on, but it will only be bit by bit by bit. And in order to really grow and make this happen, we needed to change the strategy. So we actually raised money to found this company, Integritee, and we also rebranded the entire solution. So that's
Incredible.
and now I'm kind of the technical, yeah, I'm the techie for Integritee, but the business is actually for business. Luckily I have partners who do that.
Awesome. Yeah. So you very kind of came from the ground up, like, grassroots, there from the beginning, and now you kind of find yourself in a position where, let's make something out of this, because it can be used in a lot more ways than you initially might have thought. Super exciting. Well, I don't want to like take out too much time from this seminar, because I think there's a lot to cover, and there's a lot of probably interesting things that might come up that might spark some discussions. So like usual, like any seminar, please ask your questions in the question box, and I'll kind of keep an eye on that as Alain's presenting. Then maybe if it's relevant, I can kind of interrupt him with that, if that's cool with you, Alain.
Please do interrupt me. I wish for this to be interactive, so interrupt me at any point,
Awesome.
if
Yeah,
there's a question to the.
don't be shy, guys. So I'm going to go in the back, and I will let you take it away. Why don't you share your screen?
Yes.
And I'll be here just listening intently.
So let's hope this works. Does it?
Yep, I can see it
Oh, okay.
crystal clear.
Okay.
Sweet.
So this is our new shiny logo. Well, so what I would like to cover in this seminar is um, probably there's a bit more content than we really want to dive into in detail. So it's feel free to also really mention what you would like to know more about throughout the talk here. But first, I will give you a little bit of an introduction what Integritee actually tries to solve, and how. So a very key technology for us is a trusted execution environment. So I will briefly talk about what that actually is. Then I will introduce the two main concepts that we use to combine trusted execution and public blockchain. One being indirect invocation, where kind of all the state transitions need to pass through the layer one blockchain, but are executed off chain. And the second one is the sidechain thing. That's where we are probably most unique, and that's the most recent thing we are about to release now. So a second layer scalability solution, which is based on trusted execution. Then I have three examples that we can go through, and the novelty today is this will be the first time we present our Tiracle. That's an Oracle service that will feed exchange rate information, market information into the blockchain with non-repudiation. So we don't need kind of a not an oracle in the sense where you incentivize and punish oracles in that sense, but where we rely on trusted execution to verify the authenticity of the information. The next is the Ayuna gaming sidechain architecture. That's what I actually did present at Sub-Zero already, but you will let me know if I should go back, reiterate that, and maybe tell a little bit more than I was able to at the conference. And well, the Encounter sidechain architecture is rather a kind of a conceptual study how we will continue there, because right now Encounter is focusing on just becoming a common good parachain with all transparency and everything on layer one, so to say, and kind of this is more about the next phase where we will do the sidechain thing for Encounter. So that's what is awaiting you. So let's dive in. Integritee, with its technology, wants to solve the three big challenges for blockchains, as modest as that. In a way, you have, I mean, I will talk about the tool that we use later, but I think trusted execution actually really has the potential of solving these three challenges if you can accept the trust model which is involved. But we can talk about that in a minute. So the three big challenges I see being confidentiality, scalability, interoperability. With confidentiality, I think it's clear blockchains are, well, very transparent in naturally, because if validators don't trust each other mutually, then that means that everyone needs to be able to execute all the state transitions and verify that they come to the same result. So that means they need all the information which is necessary to validate. And as soon as you obfuscate this validation, then you change the trust model of that consensus somehow. And we see a big need there, especially if we want to bring enterprise use cases to the blockchain, then confidentiality becomes even more important. Also because enterprises are bound by law to certain data protection rules, such as the GDPR in Europe. And this becomes a bigger and bigger liability. So I mean, yeah, you can well say that data is the new gold, but in a way, data is also a big liability. So it's a big kind of reputational risk if you leak sensitive data. So enterprises are very cautious about this, or should be. Then scalability, I think, well, that's an obvious one. I just like to reiterate the CryptoKitties example. We could also tell the Uniswap example for, but anyway, let's say CryptoKitties. So Ethereum is a platform that allows execution of smart contracts and allows this to anyone who pays the gas fees. And CryptoKitties is just one of the dApps that did deploy on Ethereum. And because that was a very, very popular app, the gas prices went through the roof because you have a limited resource processing all the state transitions, and the validators will just pick the ones who pay the highest gas fees. That means all the other dApps, which have nothing to do with CryptoKitties, they are actually suffering from their success, from the success of CryptoKitties. So this again might be fun in an experimental thing, like, yeah, let's try something new, decentralize it, and so on. But if you are serious about the dApp that you actually want to deploy, if it's a real business, and if you're maybe an enterprise that would like to use this as a tool, then you need some kind of a planability. And you don't want just some random funny game to kind of bring your use case to a full stop. So we need to solve that somehow, and we do provide an answer to that. And we have interoperability as the third challenge. We see that blockchains are mostly silos. And I think this still applies to even the Polkadot ecosystem, which is which is very much about interoperability. But I'm talking about interoperability among blockchain ecosystems and also to legacy Web 2 APIs, so REST interfaces, whatever, SOAP, standard centralized databases. We would like to be interoperable with them as well. And so these are kind of our three challenges that we would like to tackle. Oops, wrong direction. And our suggestion here is basically, let's take trusted execution environments, combine them with public blockchain to solve these three challenges and get public auditability about it. And what is this thing with public auditability? Trusted execution environments. Let's go into that first. That is a technology where we get hardware guarantees that a certain process is executed without any changes, and that all the data which is used by that process cannot be seen by the system administrator or by the operating system for that matter. So we use Intel SGX technology, and not all the TE technologies work the same way. So the specific information here is about SGX. You have kind of a library. It's a bit like a dynamic library that you can just take into your application, which will be executed with a special instruction. And then that will be an enclave. We call these enclaves. So that is a process which is executed in this trusted execution environment way. And this is, well, it is still a niche technology, and it's not well understood what actually the benefits are. But if you imagine, we are so used to the fact that a system administrator can see everything and can change everything and can make us believe whatever they want. And that is usually not a problem, because system administrators are people that we trust. But the problem is, if we have some kind of malware or a hacker that by any means gains administrative privileges, then that means they can do exactly the same. They can change software which is executed, they can see all the data, they can change the data, spoof anything. And so that's why we see so many leaks nowadays, right? It's even if we have very highly capable administrators today from the cloud providers, which are kind of specialized in this, we still see a lot of leaked data on a daily basis. So we would like to promote a kind of privacy by design approach where we have to treat data very, very differently and only share data for very specific purposes. And now this trusted execution environment, if I have that on my laptop here where I'm sitting, then I can more or less say, oh, okay, there is an Intel CPU in here, and that laptop tells me that something is executed in a TE. Okay, I will believe that. But if I now try to convince someone on your side that I'm executing something on my laptop in a TE, how should I do that? And that's what remote attestation is about. And so let's imagine this. We have an open source code. So somehow we agree on some algorithm which will process very sensitive data from all of us here in this seminar. This is open source code. Everyone can look at it and see what it actually does. Now we can deterministically build that code. That means that the hash of the binary which will be compiled will be the same for all of us if we compile each, if everyone does that. It's reproducible. And if we now execute that on a trusted execution environment, and that trusted execution environment gives us a measurement of that, and that's what Intel attestation services can actually attest. They can remotely verify that I am running a genuine SGX device, and they can also attest what the hash is of the binary what I'm executing in a way that I cannot tamper with it. And now there we close the loop actually. So we have Intel attestation services telling us, okay, on Alan's laptop there is really SGX with that and that software running. Then all of you can be convinced that whatever you send to exactly my enclave will be processed exactly as you expect without me seeing the data. Now, where is blockchain in all this? Because here we don't need blockchain, right? This is just a piece of hardware with special features and a manufacturer which can attest that hardware and what's running on it. The point is, we would like to open this process to the public, because the whole attestation thing of random third parties running SGX and kind of random challengers who want to know if it is genuine, that is not exactly the case. This is not really what Intel attestation services is designed for. So what we do is we verify the report which comes from the Intel attestation services in our substrate palette, which we call the T-Rex palette. That's the T registry. So we can actually verify the certificate from Intel attestation services and parse that report for certain information, like the MR enclave, which is basically the hash of what is executed, and a little bit of extra information. And so and we put that into a registry which is queryable by anyone who has access to that public blockchain. So in that registry, you will see a URL where you can talk to that enclave. So where can you actually reach that service, and a public key for authentication, so that you know that you're really talking to the enclave. So whenever that enclave is started for the first time, it will create an SR25519, kind of a substrate account, so to say. And it will send extrinsics to our chain using that account, so you always know that what comes from what is signed, whatever is signed with that public key, comes indeed from that enclave.
So can I interrupt just one
Yes, you
second?
can.
So
Please.
if I understand correctly, like really like this model is okay, so we've got Intel that is doing the attestations as a sort of standard feature of using these SGX machines, these trusted execution environments. Well, what this architecture is putting forward is like removing that trust layer, which is trusting Intel. Is that correct?
That is not correct. No, we still need to trust Intel in two ways. We need to trust their design of the TE hardware, because, well, there could be a vulnerability, and there have been a lot of vulnerabilities already discovered in the past, which have been patched by microcode updates by Intel. The most severe ones were side channel attacks, I would say, and kind of. But so far, Intel was very quick with coming up with these patches and kind of regaining the trust promises they give. But we also trust Intel not to attest fake devices. So Intel attestation services is trusted in the sense that they could have some fake devices with backdoors in them and attest these that would be in their power. Now, obviously, we don't want to rely on Intel alone. So we think our concept is even more interesting if we do a slightly different scheme of attestation, because the attestation services, in a way, is not really necessary. We could have identifiable, so or devices with unique physically unclonable functions, or with fuses burned in kind of the commissioning process or whatever. If the manufacturer of a CPU of a TE would register all these fingerprints on the public blockchain when the device leaves the fab, then we wouldn't even need the Intel attestation services. So we are kind of prepared to cover for that use case. Let's imagine we have an open source TE design, like a Keystone, for example, which is produced by several silicon fabs, and they all, whenever a die leaves their fab, they will just register the public key, so to say, of these devices on our blockchain. Then you can remotely attest these devices with only using the public blockchain.
Got it.
But that's kind of that's rather our future roadmap, right? The diversification thing. So for now, I have to say Intel SGX is the only technology which actually delivers the entire story that we would like to implement with this remote attestation thing.
There's a question in our chat asking, do we also then check the microcode patches that have been that have been implied? And
that's a very sensible question. Yes, yes, we do. So the Intel attestation services, what they attest is also the status of that enclave. So they can say, is the BIOS configured correctly? And is the latest microcode applied? So if the status of the remote attestation is okay, then that means, yes, everything is fine. The latest patches are there. The BIOS is set up correctly. Everything is fine.
Got it. Cool. Well, I'll go back off. That was great to clarify a few things.
Yeah, please. It was a good spot to interrupt, actually.
Nice.
All right. So now, what does Integritee want to deliver with all that? I mean, I have talked about the challenges, but so we really want to deliver a tool set which you can deploy and optionally use our Parachain. So Integritee is now raising funds in a crowdload to become a Kusama Parachain, but even so, this is just one of, it's kind of what we offer to use the technology, but teams can actually just take our software and use it in a different way. That's perfectly fine as well. But I'd like to just highlight why it could be interesting to actually use our Parachain once it is launched. We can enable teams to launch even with little capital. That is one reason. So accessibility in that sense. So you don't need to raise $100 million worth of tokens to just get a Parachain slot and start benefiting from that layer 0 security that Kusama or Polkadot supply. You can deploy your palettes or your runtimes as sidechains on our Parachain, and you are still entirely free how you would like to run the infrastructure. Because in our case, so there are other projects that do trusted execution stuff as well. I'm sure you know Fala, for example, which follows a very different model in terms of who runs the infrastructure for what reason and how the tokenomics work. So in our case, if you want to deploy a dApp, then you are in charge to supply the infrastructure for it. So we Integritee, we supply the Parachain and all the infrastructure that is needed there. But the SGX machines, we can supply them as a service, kind of as a company, as a cloud service, but actually we expect dApps to take care of that themselves and incentivize it themselves if they want. So the upside of this is you just have to pay for the service of remote attestation and finalizing the sidechain on our Parachain. So you have predictable cost, and that is the actually the second thing in our tokenomics, which I think is very unique. We adjust the fees you have to pay to use our service to be stable. So later in this seminar, I will present to you the exchange rate oracle, which we actually intend to use such that we know on chain how much our token is worth, and in that sense, we want to have predictable cost for using our Parachain. This is especially motivated because we would like to bring enterprise use cases to public blockchains. And enterprises, they really don't like to have unpredictable operation expenses. So that is kind of a step.
That sounds, sorry, like that sounds super useful in general, right? Like, most, like a lot of, parachains would want to have that kind of plugin, I guess, right?
Well,
I mean, obviously we can talk about maybe this, maybe that, but I'm saying like more generally, like it's a fun feature to add to your blockchain.
Definitely, it's something. Well, it's something that everybody would like to have. But the problem is, if you have a limited resource, you need some way to allocate that limited resource if it gets congested. And but I think as we don't need, as a parachain, we don't need to care for the security. So we don't, so kind of the limited resource is taken care of somewhere else. And if our parachain gets congested, that means that our service is so popular that we can afford just another parachain slot. So we can kind of scale horizontally for quite a while. But I don't actually think this will be necessary because our Parachain is only serving a very narrow use case of verifying remote attestation and providing finality. So it's not there to do a lot of heavy work. So
Right.
the heavy work will happen on the second layer. That means I don't expect our Parachain to be easily congested.
Mm-hmm.
And that's why I think it will work, that we can have stable fees, um, and not kind of, yeah, punish our users with exploding fees just because we get more popular.
Got it. Got it. Yeah.
Um, but talking about enterprise use cases, what is also important is enterprises, they don't like if they lose control. And well, decentralization in a way is about losing control, right? That's what it is about. But some use cases require the data to reside, or the computation to reside, in a certain jurisdiction. And that is impossible if we do it like smart contracts on Ethereum, because they are executed all over the world. And because we allow each step to take care of their own infrastructure, they can also have a permissioned deployment where they ensure that the execution actually takes place in a certain country, or in a certain data center of their choice, or whatever. And because it's in a trusted execution environment, that is not such a big drawback in terms of trust, um, because, yeah, because of the guarantees that the TE gives us. Okay. If there are no direct questions to that, I think I will go on and
Yeah.
talk a bit more about
Just
the
a
tech.
reminder, just guys, ask your questions, right? We're here to sort of discuss things, and that's kind of why I'm jumping in here and there. But I'll go back off.
um, so I initially said there is basically two ways how you can interact with our tech. One is indirect invocation, the other is direct invocation. And so indirect invocation is what we actually developed. I don't know. I think we delivered it 2 years ago already, under the name of Substrate. So the idea here is, if you just want to offload some computation of the chain, but all the invocations will go through the chain. So let's take an example of shielded token transactions. So let's say we have a token on in our TE, actually. So the balances are private, all the transactions should be private, and so on. Then we have our Parachain, which will do nothing more than just forward all the state transitions, all the balance transfers to that enclave. So what do we have here? We have the Integritee Parachain. We have, in this case, a single instance. I mean, this should be redundant, right? But we now have a single instance of an enclave, which keeps the balances in encrypted state. So the entire ledger is here in encrypted state. Only the enclave can read it. And if you want to know your balance, you have to hit some whatever RPC interface of that enclave directly and authenticate. So that user needs to authenticate to learn the balance of its own account. Now, let's say Alice transfers 2 tokens to Bob. Then Alice would first query the shielding key here. So that is an asymmetric encryption key. So we would encrypt our call before we send it to the blockchain, because on the blockchain everything is transparent and we don't want the public to know what we're actually doing over here. So we have we call that a trusted call, which just says, I want to transfer that much from Alice to Bob, and you sign that trusted operation, and then you encrypt the entire transaction and send it as an extrinsic to the chain. Now, in that enclave, we have a light client running, which scans all the blocks, all the new blocks on that parachain. and scans it for all the relevant extrinsics. So, for example, this encrypted call that Alice was sending will be parsed by the enclave. It will be executed on that encrypted state, and we will give finality, so to say, here to that single call by confirming it back to the chain. And now Bob or Alice can kind of tell Bob the hash of what happened, and then Bob knows, okay, Alice indeed did a transfer, and then Bob would query the new balance here on the enclave. Or Alice could even provide the plain text transaction so that Bob can kind of prove it back to the hash, which he can find here in the Parachain. Now, this is so the token transaction example here is a bit virtual, because this scales even less than what we see than if we would do a token transaction here. We get privacy, yes, but we pay for this privacy with scalability, because this call is even bigger, is a heavier transaction than it would be if it would be plain text. And we need to wait longer because it takes a detour until it gets confirmed. Um, so this is a scheme which is more interesting if you have heavy execution state transitions. So if you want to be sure that something happens on chain and triggers some whatever heavy computation off chain, then this is a good way of implementing it, because the enclave has more performance to also execute something than you would have if you just try to build that into WASM on your chain. So even if you don't care about privacy but only about kind of heavy duty computation, then this could be an interesting approach. But this is really, I mean, this doesn't answer the scalability issue, right? And that's where our sidechains come into play. Um, and I think the interesting thing here is, so why are T's a key here? If we validate a blockchain, then validators mutually do not trust each other. And that's why they need a consensus protocol involving a lot of communication. So we need a lot of network bandwidth to exchange information and prove what the others do. So it's just very interactive. Now, if we use trusted execution environments to validate a chain, then the individual validators can mutually remote attest each other, because all these, we call them validators. Actually, it's another word play to just express that it's a trusted execution thing. All these validators of one sidechain, they need to register on our Parachain, where their remote attestation is verified, and that means they can mutually challenge each other and see if the other is a real validator as well. And if they are, then they don't need to re-execute what every block. So this is a very interesting property, because we can go down with block times by a lot. If we just need a handful of validators to just give availability, because the security actually comes from the TE, then we can go to sub-second block times. And the demo that I will do later is in the order of 300 milliseconds block time. But that obviously, I mean, there is a bit of networking involved, and it really depends on your deployment and how far away the validators are in terms of networking.
So,
infrastructure.
I've got a
Yeah.
question here to
Yes.
something to clarify on my end. I don't know if others might have the same sort of thing. But so when you're saying, you can go to very short block times, you're basically talking about block times as these sidechains understand it. That really, like, the parachain doesn't really have the same concept of that block time. Is that correct?
Sidechains, I will go into the block format of the sidechains because it's very different from how the parachain would do a block, right?
Yeah, because basically where I'm coming from with this question, it's that um, if you're a parachain on a relay chain, you need to be and I'm abstracting, it could be any relay chain. Well, you need to have the same block times as that relay chain,
Yes,
because
agree.
otherwise the relay chain won't be. Otherwise, you just will have like lots of mismatches and consensus and stuff like that, and transactions lost, etc. So my question is, if I understand correctly, in your architecture, the very fact that you're kind of including this sub-second block times, by definition, it's not the same type of blocks that the consensus understands, right?
No, and it's not, in a way you could understand our sidechains as, or you could understand our parachain as a nested relay chain because we are kind of the next level of hierarchy, but that is not exactly true in the security model because the relay chain validators actually re-execute all the blocks, all the state transitions in order to validate these blocks. um, the beauty of that relay chain concept is just that validators can do that in parallel. That's why we can cover for 100 parachains. We don't do it like that on our parachain because our parachain doesn't validate anything other than remote attestations. So that means the trust model of our sidechains really is based in trusted execution environments that we use for it. And our collators, they do not know the logic to validate the blocks of the sidechains. And that's why we can have very different definitions of blocks on
Mhm.
our sidechains. And and because we don't need to re-execute anything, a block in our case is actually just a diff on a database that you can
Got it.
also, so it's a diff on the hash map of the state actually. So it's not a series of state transitions that you need to re-execute to come to the new state. It's really just a diff which you apply to your state, and that's why everything can be accelerated by quite a bit.
Cool. Super interesting. I'll get back off.
All right. So that's, yeah, but I think that is the most important thing to understand in terms of how our side chains work. So every 300 milliseconds we have a new block hash which is sent as an extrinsic to our parachain, and once that parachain, or once these extrinsics are finalized on our parachain, then the side chains blocks are finalized as well. And obviously, we might not want to finalize each single block, because if we need to wait 12 seconds, we can just finalize a digest of the last, whatever, 30 blocks. So it's not strictly necessary to kind of anchor every single block in our parachain. Well, that will be. I mean, we need to see how people will use our tech. Um, so we give all the freedom in that sense to do as teams please. But that's where fees will be paid in our tier token, right? When you register your validators, and you need to frequently re-register these validators because we need to be sure that you have applied all the patches. So let's say every 24 hours you will have to re-register your validator, and if you want finality on your sidechain blocks, you need to send extrinsics to our parachain, where we will charge fees for that in tier token as well. Um, so, well, actually, this would have been the slide to explain your question. um, so we have layer one, which is the Integritee Parachain, and we have, let's say, every 12 seconds we have a new block. And during the same time, we here have just two validators who take rounds in producing new blocks. So currently we are implementing the Aura slot scheduling, but that might change in the future. But for now, that's fine. So if we have two validators, they will just produce block one, then block two, then block three, block four. They will just alternate. And here you also see why we need the finality layer here, because this is still a peer-to-peer network here among these validators. That means we can have partial networking eclipsing of validators. That means we can have forks. Because if the validator 2 fails to produce or to broadcast a block to validator 1, then there will be a timeout, and then sidechain validator 1 will produce the next block instead of this validator. And then if the network reconnects, then you obviously have a fork because you have two different versions of the chain. And that's why we need this finality layer to actually yeah, so for block production we don't need it, but we need it for finality. So that's basically what I wanted to say. Yeah, let's we can maybe come back to the very to this if there's time at the end. So our block format here is, I think, the only really important, so that there's no big surprises here. It's pretty much like Substrate does it, with the very big difference over here. So the state update is actually just a diff of key value pairs to overwrite in the state. But it's then signed by a TE, and that block author needs to be registered on the Parachain. So this is how sidechain blocks are different. I think here I can go a little bit quicker because we already talked about unpermissioned and permissioned operation. So you can either have everyone run your software on they just need an SGX machine, and then they can participate in validating your sidechain, or you can say, no, I want to be sure that it's only in jurisdiction XYZ, and then you run, or only maybe, and that's an important one in the trust model. Maybe you want to be sure that only SGX machines which are operated in a professional data center are used, because so the side channel attacks that you can do on SGX and probably on any kind of trusted execution environment, they are even easier if you have physical access to the devices, because then you can do like fault injections by modifying the voltage supply and so on. So you can do a lot more sophisticated attacks if you have physical access to the machine. So it might make sense to have kind of a semi-permissioned operation where you say, well, any entity can run um, our validators, but the machines must reside in a certain data center. And that's where Intel Attestation Services gives us a hand, because they are kind of the root CA for these attestations, but data centers can be CA too. So you can have a attestation that says this is a genuine SGX machine and it runs in the Azure cloud, for example, or in the OVH cloud, or, yeah, for that matter. So that is possible technically. And that might be an interesting use case to just avoid the most critical vulnerabilities of these devices. And I mean, Intel has been very clear in the sense that they kind of exclude physical access from their trust model, which is kind of a little bit of a weak statement, but it's just the case you have a bigger set of vulnerabilities at your disposal if you want to attack a machine, if you have physical access. Yeah, and that brings us to the deployment options. So just to give you an idea of what it means to actually run an SGX machine, because my initial example with my laptop is obviously not kind of the professional setup that you want for your deployment. What we played with, so I mean, we don't want to advertise anything in particular here, but it's just what we have seen to work. And there are more and more cloud providers providing bare metal machines. And bare metal is important for us because we don't want any hypervisors in the game, because they actually weaken the trust model. So, for example, the OVH Cloud has a simple bare metal machine where you can enable SGX for around €100 per month. So it's definitely more expensive than just some, well, random virtual machine, but still reasonable, I would say. And if you want to run our software, then the ones who operate need a commercial license with Intel. I'm not sure if that will be the case for a long time to come, because Intel actually changed their policy there. But for now, it's the case is, if you want to operate it, you need to be a legal entity. You need to obtain a production license with Intel, and that is one more reason why our public auditability, public blockchain approach is very interesting for end users, because end users will never get such a license, and we can just kind of provide the layer where the entities running the devices can show that they comply with,
Okay,
well, yeah.
so there's a question here
Yep,
that I think is very relevant right now. So I'm just going to ask it.
please.
It's, why should a project need to execute the remote attestation on your Parachain? Can't it just integrate the Integritee e-registry palette in its runtime?
Yes, it can. Absolutely, it can.
Right. So, but
Um,
from what you just said, like, I think that the answer to that question is, of course it can, but the sort of, getting access to a network where there are already registered secure enclaves, Intel's SGX secure enclaves on the network, well, you don't need to worry about the layers around getting a certificate and whatever between those workers and Intel. Is that
well,
correct?
that I would say is not even the major reason. I think a lot of teams might rather focus on developing their business logic, and maybe even have a service contract with Integritee to say, hey, here is our software, which is which is built with your framework. Please deploy that and operate it for us. So that is one of the use cases that we definitely see, and that we see with the few projects we have worked with so far, that seems to be interesting for many. And thanks to the TE, Integritee is not a trusted party in that game, so to say. But the reason why I see that our parachain is attractive is you just don't have to care about this anymore.
Mm-hmm.
So it's rather a convenience to join a working ecosystem which is maintained, because you know you 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 always need to catch up with recent developments. You need to maybe have some kind of key rotation with IAS and so on. Maybe maybe there will be new kind of checks that you want to be sure that such and such is the case. For example, if they come up with a new generation of devices which
Yeah,
is
yeah.
attested differently and so on. It's just
Yeah, I mean,
it's
you're
a
providing lots of
maintenance.
services around this
Exactly.
tool.
And if so, If there is another Parachain team which already has a Parachain slot, yes, sure, they can use our palette. They are, I mean,
Yeah.
it's that's what open
Cool.
source is about, right? You can
See,
you
I
can
think
you
you,
can use it, but then you have to maintain the whole thing,
of course,
right?
yeah. Yeah, I think that's a great answer to that question. I hope that answered that question for the person who asked it. There's one more. I mean, I don't know how close we are to like just diving into demos. If this is a good time to ask like maybe a couple high level
We
questions.
are very close because the next slide is kind of let's go into the demos.
Okay,
So
perfect.
yeah.
So I guess because then we have like maybe, yeah, like, so demo time should be kind of just demo time. So maybe it's a good time to ask these few questions here. And by the way, I put up a poll asking folks here if they're planning to build something requiring a trusted execution environment. And I mean, there's a good mix of votes. There's not many people that have actually voted, but a couple of them are saying yes. A couple of them are saying not really, and others are saying, maybe. But I think it's always interesting to hear what kind of projects are looking to use trusted execution environments. So guys, like, feel free to share what your ideas are, because I'm sure Alain would also be interested in hearing, and you can always kind of connect with him after the seminar. So uh, that was a little segue into this next question here, which is, in terms of performance, what are the advantages of, this is a question I had too, actually. What are the advantages of using TEs over zero knowledge proofs, if any?
Yeah, that's an important one in such a
Yeah,
seminar.
that's all I was thinking about. Like, I was Googling, like,
um,
but yeah, please.
and I mean that's the obvious alternative, right? And well, for certain cases, ring signatures as well, which are a little bit simpler than zero knowledge proofs. I would say if what you want to do is simple enough to use to build a zero knowledge proof around, then go for it. I just believe that zero knowledge proofs are very academic still. They don't generalize really well. You need a PhD to kind of wrap something new into a zero knowledge proof. So general computation is not yet readily available for let's say general developers. Um, and Ts are actually a commodity hardware thing that we can use today, which is pretty mature. Which you, I mean, we code the whole thing in Rust, and and we did all the wrapping, so you can write your palettes or even your ink smart contracts or your EVM smart contracts and execute them in our system. So it's a lot more generic, a lot more accessible. And there is another thing: zero knowledge proofs generally, and ring signatures also, come at the cost of scalability in most cases. So if you wrap a single token transaction in a zero knowledge proof, then the transaction is harder to generate, it is bulkier, and it is also harder to verify than a transparent one. Um, of course, there is ZK rollups, which are kind of a very interesting thing as well. So you
Mhm.
can offload computation and just prove that you computed something, and just commit a ZK rollup to the chain. And you can even have kind of optimistic setups where you just assume that it has been done correctly, but you can take samples and you can blame and prove that someone misbehaved. That's all very interesting, but it's also very, very complicated compared to what we can do with TEs.
Yeah, super interesting. Yeah, thanks for answering that. Just like, there's another question that might be relevant. Well, two more. So, person is asking, does it still work when the hypervisor comes into play, or is it completely not possible? So I'm not very familiar with the hypervisor, so maybe you could give a few words on what that is.
So when Azure, for example, gives you a virtual machine,
Mhm.
then that is executed on a server in a virtualized manner, so that you kind of have your own machine in that virtual machine, and that's where the hypervisor comes in. The hypervisor takes care of scheduling multiple virtual machines on a single hardware.
Hmm.
And Azure is the example which has trusted execution virtual machines in their offerings. Um, the problem is, if you use a hypervisor, you have additional attack vectors to do side channel attacks. So even if you are on this on one hardware, and you have two VMs, then one VM might learn something about the other.
Got
But
it.
to be honest, this is not my strong. So I'm not an expert on how to attack SGX. So this is about as far as I can go in giving an answer. Um,
Cool.
yeah,
The last question we have here is, can a commercial SGX license be revoked?
yes, it can. It can. Because basically what you do is, well, Intel has a contract with you. They can cancel that contract, and you have to supply your public key that you use as a vendor key to sign your enclaves, um, and they can revoke it.
Yeah, got it. Yeah, I mean that I think that's kind of like where we're today is certainly not where we want to be. Like, I don't know, like 2 years down the line.
Exactly.
With
It's really just the first step.
Yeah,
I mean, yeah,
cool.
definitely.
Okay, I'll let you dive us into
Okay.
Demo
Okay.
land. I've got my submarine suit on. You can't see it, but
Okay.
I'm ready to go.
Okay. So let's start with this Oracle, because so if you're interested in the gaming and sidechain thing, I'd say go to the Sub-Zero recording. And so we'd rather spend the time on this T-Oracle demo today. Um, because I see we only have some 20 minutes left. What is the T-Oracle? So in our setup, we have some relay chain, the Integritee Parachain on top. The Integritee Parachain has this pallet T-Rex, and we have this enclave. Let's say this is a single instance. This enclave has the logic to attest itself, so to say, to that pallet T-Rex. So actually, I mean, there is a service around this enclave who will kind of handle all that. But so this enclave will be registered in this pallet with its MR enclave, so we know what software is executed here. Now, the interesting thing with the TE is that if we have an HTTP client here talking to some REST API with a TLS connection, then we know that this enclave actually authenticates the server of that REST API. So CoinGecko has an SSL certificate. They run a REST API. Our HTTP client authenticates that. That means we have non-repudiation on the information we get from here. But the non-repudiation is only verifiable to that TE, but not to the rest of the world. And that's the problem with SSL. There is actually no, or not yet. I mean, there are proposals that SSL or TLS could actually have non-repudiation as well, but so far we don't have that. So our Oracle provides that service. So it authenticates CoinGecko, it queries information from CoinGecko, and it writes that through an extrinsic to our T-Oracle palette. So this is a palette which just takes the exchange rate of our tier token to the US dollar. And in this demo, it will be the dot because tier is not yet listed, so we cannot query any exchange rate. Yeah, so as simple as that. I think we just go to the demo. where we can see that. Okay, let's start it all over. Did you see what's actually happening? Okay, so I'm saving us the trouble of really launching a parachain and the relay chain. So it's just a solo chain with our T-Rex and T-Recal pallets in there, with some log filtering here for simplicity. So that's just a plain substrate node. No SGX, nothing, no special requirements on hardware. And it's producing blocks now. And now we are on the TE hardware. Let me just clean up here and run our T-Recal service. And let's quickly go and see what the actual exchange rate is right now. We are at $42.44. And so what you see here is the enclave. Here is the Emmer enclave, so that identifies the software, and it is registered. Yeah, okay, now it's already gone. It registers itself on that chain, and now it starts producing extrinsics, and each extrinsic. Oh, that's funny. $42. Why is it 42 now? Oh, okay. I think it's there are different exchange rates that you can query. And I guess it's either 42, 47.
Yeah,
Oh,
that's
42. Yeah, okay. It fits. It fits. Okay, so you see this service queries one dot equals 42 US dollars here out of the enclave through a TLS connection, sends an extrinsic over here, and in our palette you see the extrinsic is registered, and we have updated. With every block, we get an update of the exchange rate. You also see that not every block has a change, but that actually has to do with the API. So we just don't get new information every 6 seconds. But it's as simple as that. This is the oracle that we will use to adjust our parachain fees to have stable fees.
super cool. Can we look at sort of what's going on with like using so fetching that information? What are the APIs like and the endpoints like getting that information, and then what's going on in that journey from that information to actually being in a block or in a sidechain block?
Sure. So let's quickly see. Where is the API doc? Well, anyway, I mean, you can imagine it's a REST API where you can query any information. Now, in our enclave, we have. Let me dig up that slide again so we can.
So by the way, I shared a link of the Integritee runtime. I always find that it helps to kind of understand what palettes are in there, and it was, I think, a good
Yes.
Sort of resource as we were looking at that slide with the different palettes.
Sure. And actually, so if you're interested in this presentation that I can share later, we have a few pointers into code where you kind of also see how many lines of code you actually need if you start with our framework from zero to including a new palette to executing it and all. So we have a few pointers here. But
yeah, cool.
So
do you have that link? Do you want to just post it in the chat? Because I think there must be several of us here that are thinking about maybe how to use this kind of infrastructure in
sure.
our own projects, right?
I will share the link of that presentation, I guess, which is the most simple thing. Share. Sorry, there we go.
Yeah, I think there's a lot of interesting applications that can be or sort of can leverage this sort of architecture. Someone in the chat is talking about a credit rating system and a credit scoring registry. Cross country, like you're talking about infrastructure that needs to be privacy and confidentiality first, right? So that's super interesting to see people sharing their ideas in the chat. Cool.
So maybe back to your question, I'm not sure which part would you like to go deeper into. So
I think for the sake of time and also for the sake of keeping things sort of possibly like what the most interesting for people watching this video is like, okay, so how can I get building with this, or what are the bits and pieces to be
yes,
most sort of like accustomed to understand what's going on? Because
yes,
what you just
yes,
showed us was really cool because we were able to see it all happening in real time and
yep.
in your terminal. But I guess where I'm most interested in is that second bit on
How
the
to build? Okay.
yeah, and like what's happening on the TE side of things. Because I think a lot of us are familiar with, running your own node
Yes.
and putting in pallets in your runtime. But then the question here, what's interesting is what am I doing when I'm trying to configure my own side chain, right?
Okay. Let me take this example here. So that is now the gaming example that I used at Sub-Zero. So I won't go into too much what it actually does, but what we have here is we have some palette that Iuna wrote, and it contains the logic of rock paper scissors. So it's
Yeah.
really just let me see
I'm going to
here.
share the link of Iuna
Yeah, you see it that the link is
runtime.
in the slides that I just shared. So you can just click on it. So is nothing fancy. It's really just, I mean, it's kind of a it's a palette with only a few dispatchables. It has, oh, let me, we're still at the error. Sorry, new game. So new game is an important one. Choose, so you have to choose rock, paper, or scissors. So these are just a few that we will wrap in our state transition function. And so here what you see is we now have this palette. We wrote it and
Alain,
we
are
debugged
you
it with,
sharing your screen right now?
oh, sorry.
I couldn't tell because it was pretty captivating, but then I realized you might be sharing your
Okay.
thinking.
Okay.
Yeah,
Yeah. Sure. Sorry. Yeah.
no worries.
Too bad. Too bad. Um, so
Oh, sweet. Yeah.
you have this palette and you have debugged it with the node template, whatever.
Mhm.
Now you go to Integrity Network SGX runtime and you integrate your palette in that runtime. And let's just look at the diff of what that actually means. So you just, yeah, in the toml file, I mean, you know how that works. You add that and you add it in the construct runtime part. So in, and this now is not the parachain logic or the layer 1 logic. This is the layer 2 logic. So this is what will be running your sidechain. That's
Super interesting.
that is the runtime. Yeah, exactly, of your sidechain.
Yeah, that's why it doesn't have any governance. It's
Nothing.
purely just
Yeah.
block execution, and you got a transaction payment module in there. But yeah,
Yes.
pseudo access balances. Cool.
Yes.
Interesting. Yeah.
And there is actually not much more. So you just, I mean, yeah, you wrap your thing in that runtime. The syntax is exactly the same as with Substrate node template. And then you go over to worker, and worker is kind of the thing, the service you will execute on an SGX machine.
Mm-hmm.
And if you want to, if you want to do that, um, there we also have a diff. Yeah, the log file is not very interesting. Well, again, you want to somehow include that in your state transition function. So what we do here, yeah, let's look at, not this one. Let's look at, yeah. You need to write glue logic because you now have a new interface. You don't have the substrate JSON RPC standard thing. We do it almost the same way, but you have to wrap it, because we need to go from the outside into the enclave into your runtime. So you have to write a little bit of glue code. And that glue code looks a little bit like that. You have to define what are the trusted calls that I would like to execute or to invoke. And you see, our template already has the balance wrapped. So whatever you want to do with a token on your sidechain is already provided. But now you add your dispatchables. So RPS palette new game, choose and reveal. And the first argument is the signer, and the second one is whatever argument your dispatchable takes. And then you need to wrap that. So the people who have been digging a little bit deeper in Substrate might recognize this. So we now have an enum with all the dispatchables and the arguments, and now we actually, outside of the enclave, we verify the origin. Because anyway, I mean, the call comes in encrypted manner. So first we need to decrypt it. We need to verify the signatures, and then we will actually dispatch the call. And we do that by digging into our runtime RPS call. So that is the wrapper for calls, for all the calls to the enum of the RPS palette. We have our runtime and the new game. So this is really directly the dispatchable of our palette, and we call the dispatch bypass filter, which is a substrate functionality. But usually you don't see that kind of thing, because if you develop your own palettes, that's all abstracted away from you. But here you need a little bit of wrapping that you need to do. Yeah, and so you see, this is just about how much code it needs to include a new dispatchable from a new palette. You also need to write a client for it. So what we provide is a Rust command line client, which is based on Substrate API client. And there you have to add all these dispatchables as well, of course. So for example, you have the command new game. So this is really a command line command. So you say, Integritee client, new game, and then you say who is the creator and who should be playing with what opponent. And then what you need to do is basically this. So you create a new trusted operation, which is a trusted call of the flavor RPS, or of the one of new game with a few arguments. You need to sign it, and you need to convert it to a trusted operation. And that conversion actually abstracts away from you all the wrapping, encrypting, and so on. And then you just send that operation over a JSON RPC interface to your sidechain validator, and you can watch your extrinsic be included in your sidechain.
Cool.
Well,
That was a lot.
I can just invite you to check out these, because these PRs are kind of really, they show you what is the difference from our main branch to what it looks like if you do something with it. So I invite
super
you
helpful.
to check that out. Yeah.
I put a link in the chat on that PR.
Great,
I think, you guys should check it out. But so, like, quickly to recap, I mean, just looking at your organization on GitHub, we've got, So the first place we're looking at is the SGX runtime, right? So that's where we're putting in these palettes. So specifically,
well, that's the most boring part actually, because this you
yeah,
already know everything from Substrate.
yeah. So it's
but
basically
yes,
a
that's where you
substrate
start.
node that doesn't do consensus and finality. It just takes in or it's able to process extrinsics and like shoot back an extrinsic onto an actual substrate chain.
It's just a state transition function actually,
Yeah,
right? Which
right,
is
right.
compatible
Cool.
with Substrate. Yeah.
Compatible with Substrate. So then the second thing you did is we went into the worker repository, right? So the worker repository is where all of this like kind of customization happens, where you write your own client. And then we looked at this app-libs file. So and then the final layer is, well, that's actually it. But the first one
Well, the
I
client,
missed.
the client side, you need to do that. Yeah.
The
Yeah,
right, yeah, cool.
yeah.
But and the very
Because we
first
don't
one
have
is
we don't
Substrate.
have something like Polkadot.js API already ready made for you. That's not. I mean, we will get there eventually, but we are not there yet to have that comfort layer. So right now there's only the Rust CLI client, and actually. Well, we have JavaScript wrappers actually already for Encounter built that you could also use to build Flutter apps or web apps or whatever. So
Cool.
that exists, but it's not yet at the comfort layer where you might know it from Substrate itself.
Right, right. I have a much better understanding, I think, on the architecture, and but more importantly for me, it's like, how can I get started just playing around with this? And I think you did a good job, like giving us what that journey looks like.
And we have tutorials on our, so it's book.integritee.network. That's where you, I mean, it's not, but part of that is outdated, but still there are a few good.
Cool. Yeah, I'm going to reshare that link.
I will.
Sweet.
Oh
yeah, thanks.
So there we have a few tutorials that you can play through. Where you also, if you don't have an SGX machine, you can do the Dockerized software emulation demo and play around.
Cool. There's a question in the chat asking, is there any chance you can show a game transaction using Integritee?
A game transaction.
I think the person means like the demo, the game demo, or the tic-tac-toe demo.
Of the rock paper scissors.
Yes. Yeah.
To be honest, I really I will have to run in just a couple of minutes. We can quickly let it run because it's all prepared. But
okay, cool.
I guess
maybe
that
that's a good way to end this.
That so we can end it with some command line stuff, which is nice.
Yeah, love it.
Okay.
Need some popcorn.
So let's look at this demo. So I will stop this demo here. We don't need that anymore, and we go to the
quick
rock
question
paper
while you're doing
scissors.
this. So basically, can you on this sort of like nested chain side, i.e., like the side chain state transition function side of things, can you just like crank up minimize the block time on that level? Is that what you would do to bring it to 300 milliseconds or whatever?
Well, this is actually to the side for the sidechain to define what the block time should be, right? So we don't.
Is there, how do you do that? Because like I'm thinking like benchmarking wise, right? Like how are you finding what the perfect middle ground is per application or whatever? Maybe you don't have these answers now.
What we know, well, I have to say we lack the experience of all of seeing many use cases. What we do is we just time box each single extrinsic. So we just measure how much time have we already used for that block and how much time do we have left. So I mean, basically this is what Substrate does as well, but Substrate does it in a more sophisticated way. We are not yet involving the weights into that. So we we just execute it, and it's in our case not so important because not all the validators need to repeat the same execution. So it doesn't matter if one machine is a bit faster and the other is a bit slower. It will just be, well, the slower validator will just include less extrinsics.
Got it.
All right. So we now have the well, wait, why are we not? Oh, okay. I'm sorry. Let me think we need to. I would like to see the sidechain blocks produced here. Well, this demo has been lying around for a while, so I hope it will it will actually work. If not, then I suggest you just revisit the Sub-Zero video. Maybe Sasha, you can share that that video in the chat as well. Okay, here you see we are producing sidechain blocks and about 3 blocks per second now. But we're not doing anything with it. So let's play rock, paper, scissors. Okay, this time it works, and boom, the entire game is already done. And what has happened here? So this was pretty quick because all the steps only took like 300 milliseconds. So first, we initialized some balances. That is the boring part. But then Alice starts a game against Bob. And that gets included in a certain sidechain block. Alice chooses a weapon. She chooses rock. Bob chooses paper. And then, and that actually doesn't really make sense here, they reveal, because the palette has been written with transparency in mind. So the palette would even make sense on a transparent blockchain where everyone sees what the other sends, and that then rock, paper, scissors wouldn't be any fun if you already know what the others do. So actually, if you choose a weapon, you just send a commitment to the chain, and then you reveal what that commitment was. So basically, it's a hashing plus salting function. But anyway, we use that palette and we do the reveal thing, even if we don't actually need it. If we use our T, and then we query the result and we see, okay, player 1, Alice, lost. Yeah, because paper wins against rock. So that was the very quick thing. And if you want to learn more about the use case of what is actually done here, then Sub-Zero is the place too.
Yeah, Alain, thanks so much. I know you need to run. This has been super cool. For those that are curious about it, check out Integritee's docs. There's a bunch of links in our chat. And yeah, I'm excited to seeing like more solutions to kind of using this architecture. It's very novel. Like you guys are the only ones really doing it that way, and that's like definitely exciting and sort of opens up new avenues for people building things, right? And so really happy to be able to share this with the community today. And really with that being said, do you have any last words before we sign off?
No. It will be advertisement, and that's what we're not here for, right?
Yeah, cool. Yeah, no, I love these seminars to like, you know, we're all building different things, and it's great to share what we're building. And on that note, there is a Substrate Seminar. There's a Substrate Seminar chat, and I'm always looking for people that are interested in sharing what they're building with Substrate. So please reach out. Alain, again, thank you so much for making the time today, and I look forward to what's to come next. Yeah, with Integritee.
Cool.
So with that said, I'm going to sign off. Thanks so much, guys, for attending this seminar.